Good morning, everybody. Let me know if you can see the do now up on the screen. It says that sharing is back, so let me know if you can say I can see it, or you can just raise your hand. Good. Thank you. Since that took a little time away from us, I'm going to get started with sharing the answers for the do now. So this is review from chapter 4, part 2, where we did orbital diagrams, electron configurations, and periodic trends. For the first question, you have to draw an orbital diagram. I usually do lines because lines are easier than boxes. So sodium has 11 electrons. We're going to fill the 1s first. And remember that with these orbital diagrams, we're not just representing where the electrons are, but their magnetic spin. So if electrons share an orbital, they have to have opposite spins. When it comes to filling the 2p or any other sublevel that has multiple orbitals, you want to go through and fill them all halfway first before you fill them up all the way. You never want to pair electrons that don't have to be paired. So if you count those up, that should be 11 electrons. So that's 2 plus 2 plus 6 plus 1, which certainly equals 11. For the abbreviated electron configuration, if you were able to do it, what noble gas did you use in your abbreviated electron configuration? Yeah, you're going to use neon. And then the only thing that we have to do is fill in the difference between neon and sodium, which is that 3s1. And just as more review, we talked about valence electrons. These electrons in the electron in the 3s orbital, that's the valence configuration. So the valence electron configuration for sodium. And finally, which element has lower ionization energy, sulfur or chlorine? Which one is it? Should be sulfur. So as you go across the periodic table, your ionization energy increases. As you go top to bottom, when we're going down a group, your ionization energy decreases. Sulfur and chlorine are in the same period. So that means that sulfur is going to be lower in ionization energy than chlorine. Are there any questions about the do now? Yes. It's just electrons. I just threw that in there as another bit of review. Any other questions? So before we get started with chapter 5, I wanted to just throw out there that I updated your mastering chemistry grades. I said I'd do that every 2 or so chapters, just so you have an accurate understanding of where your grade is. So that grade for mastering chemistry will fluctuate as you complete more assignments. So if you do really well on one assignment and then you miss an assignment, that's going to be reflected in your mastering chemistry grade. And likewise, it's going to affect your class grade. So with that in mind, please make sure that you keep up with your mastering chemistry homework and quizzes. I try not to bog you down with the chapter check-ins, especially if you have an exam coming up or something like that. And I try to make the check-ins short so that they don't take that much time and you can kind of do them along with the YouTube lecture. It's really my only chance to give the majority of the class feedback on how you're doing. So that's why I do the chapter check-ins. It's your participation, but it's also a way for me to give you individual feedback if you don't feel comfortable, answering questions and things in the chat, or if you don't come to office hours. So please, please, please do your mastering chemistry homework and quizzes. It's 40% of your grade. That's a lot. If you need help, office hours, or you can set up an individual meeting. So check out your grade, and then if you have questions about it, let me know. Any questions that I can answer now about grades or in general before we move on to chapter 5?
Yes, ma'am.
What's your question?
So, I'm not sure if you said this yet, but do we have to do the replica evaluations?
You do not have to. You're not required to. But if you don't make a certain grade on your homework assignment or on a quiz, then you have the opportunity to do some practice that's targeted towards the questions you missed or that you struggled with, and you can recoup some points. So it's up to you, but you're not required to. You're welcome. Any other general questions? Otherwise, you can just say you're ready, and we'll start with chapter 5. Okay, so there's another question in the chat about the dynamic study modules. Those are extra credit. So if you do not do them, it will not affect your grade. However, if you do some, it will only help your grade with mastering chemistry, and it will help you practice for the exam. So you can do some, however much you do, it helps you. It's added towards your grade for mastering chemistry. And it's not a bad tool to use if you know there's a particular topic that you're not good at, like conversions. So it can help you practice without affecting your grade negatively. It's also a good tool to use to help study for the final, because there's going to be all of these dynamic study modules with all these questions that you can use to refresh yourself. So just keep that in mind. Even if you don't do it during the semester, the time in between the end of classes and the final, like the week of finals, that would be a good time to use those dynamic study modules to practice and get ready for the exam. Does that answer your question? Great. Okie dokie. So it seems like a couple of people are ready. You're very welcome. So let's get started with chapter 5. Chapter 5 is on nuclear chemistry. The YouTube video is up. I'm going to do a very abbreviated, cover the topics that may give you the most difficulty and make sure that you at least get an introduction to nuclear chemistry. I will put out there right now, there's a section on medical applications that we're not going to cover too in depth in the live session. So you will need to watch the YouTube video for that, because you're going to have questions on that for your homework and on the exam. but it's something that it's not really concepts. It's just going over different types of scanning and imaging technology and how they use nuclear chemistry. So just putting that out there. This is not a substitute for watching the YouTube video. Okay. So as the title suggests, we're going to be talking about radioactivity. And radioactivity is a natural thing that we occur in everyday life. So if you like bananas, there's radioactive potassium in there. Radioactive isotopes occur in larger nuclei. So it's literally everywhere. It's just not all going to kill you. So radioactivity comes from unstable nuclei. So you've got a nucleus that's got all these protons and neutrons, and all the protons are positively charged. Normally, things that are all the same charge don't want to hang around together. So there are nuclear forces that keep the protons and neutrons together. But when we're talking about elements that have an atomic number of at least 20, in addition to carbon and hydrogen, then we're looking at situations where the nuclear forces can't offset the repulsions between the protons. So, to stabilize the nucleus, that atom is going to emit small particles of energy, and that energy is called radiation. There's different forms of radiation, and we're going to talk about these. Alpha and beta particles. There's positrons. And then there's just pure energy like gamma rays. So we're going to talk about each of these forms a little bit. Talk about some of the protective gear that you would need if you're working with different radioisotopes and things of that nature. So radioisotopes, we talked about atomic symbols already. So this is really a refresher of that from chapter 4. A radioisotope is an isotope of an element that emits radiation. And you can have more than one element, or more than one isotope, of an element that's radioactive. And just like any other isotope, you want to include the mass number in its name. So the example that's shown is for iodine 131. The 131 is the mass number. The other number that's shown in the atomic symbol is the atomic number. Just as a quick refresher, where do you find the atomic number? If I don't give it to you, where can you find the atomic number? On the periodic table. That wasn't a trick question. You can always find the atomic number on the periodic table. It's that top number, always a whole number. So you're going to need to remember that as we're going through and doing some practice problems, that you're going to have to use your periodic table to find the atomic number quite often. So are we good with radioisotopes and atomic symbols? This is kind of a recap of chapter 4. So let me know, thumbs up, I'm good, something like that. All right. So these are the forms of radiation that we're going to be talking about. And there's a couple of more forms of radiation that we're going to talk about that you kind of already know about. So the first one is the alpha particle. So the symbol for that is this, kind of looks like a fish. That's the alpha. When you're representing it in a balanced equation, it's actually a helium atom. And you will need to know all the information in this chart. So you can print it out and put it in your notebook, or if you like to write things out, this would be a good table to copy into your notebook. You're going to need to take note of the mass number and the charge, because that's going to be helpful when we're writing balanced nuclear equations. The beta particle is essentially a high energy electron. And its atomic number is -1, because its charge is -1. When we talk about balancing nuclear equations, we'll talk about what that means in terms of balancing and figuring out atomic numbers and mass numbers and things like that. The positron is pretty much like the opposite of a beta particle. So it is a high energy. It's not an electron, but it's got a positive charge. You can almost think about it as like an anti-electron. So its atomic number is +1. And again, make note of these symbols because you'll need to recognize these. Gamma rays are just pure energy. So when you emit gamma rays from a nucleus, you're not changing anything about the atom, you're just releasing energy. You can also release protons and neutrons. The way that we represent a proton is a hydrogen atom. So it's got a mass number of 1, and it's got an atomic number of 1. And then a neutron, you already know what that is. It's a neutral particle, and you can emit a neutron to stabilize a nucleus. So you'll need to know all of the information on this chart. Are there any questions about what you need to know, or do you need any clarification about these different particles? If not, you can let me know that you're good and we can move on. Alrighty, we can move on. Here are some of the properties. The properties here are only focusing on alpha and beta particles and gamma rays. And what we're really looking at is how far can they travel? And then in terms of protection, what do you need? So how far can these particles travel in air? How far can they travel through tissue? And what kind of shielding you need. And then we've got examples of sources. Alpha particles are big. So it's a helium atom. They do not travel very far. They don't travel far in air, and they don't penetrate very far through tissue. So you need pretty minimal shielding for alpha particles. They literally can be stopped by paper or just the clothing that you're wearing. You don't need any special protection. Beta particles travel a bit further. So they can travel a few hundred centimeters. And they can penetrate tissue quite a bit better than alpha particles. So when you're working with a beta emitter, you're going to need heavy clothing, lab coat, gloves, for sure. Gamma rays, these are the most dangerous. So they travel pretty far in air. We're talking about meters, okay? All the other two were measured in centimeters. Gamma rays can travel 500 meters. That's quite a distance. And they can travel literally straight through your body. So they can travel at least 50 centimeters. That can absolutely get through your body from one side through to the other. So for shielding, you need something really, really thick and dense, like lead or thick concrete. So you'll need to know not necessarily exactly how many centimeters or meters a particular particle can travel, but relatively speaking, alpha travels the shortest distances, gamma travels the furthest, that kind of thing, to be able to compare, and also to be able to talk about the type of protection that you need depending on what the particle is. So is that clear what you need to know from this table? Okay. So let's just do a quick learning check. We need to indicate the type of radiation that is protected against using each of these. So if you're wearing heavy clothing, which of these types of radiation are you protected against? So heavy clothing, and I'll just kind of walk through the first two. Heavy clothing, well, alpha particles are pretty much, as long as you're wearing clothes, you're protected from alpha particles. So heavy clothing will absolutely protect you against alpha particles. It'll also protect you against beta particles. Will it protect you against gamma rays? Will heavy clothing protect you against gamma rays? No. No, it will not. So for A, it's only alpha and beta. What about B? Which type of radiation is stopped by paper? Alpha, and that's it. The others will absolutely penetrate through paper. We'll lump lead and thick concrete together. So which type or types of radiation are protected against if you've got lead or thick concrete? So all the types that we've listed. Alpha, beta, and gamma. You'll be shielded if you have lead or thick concrete. So this is an example of the type of question that you'll need to do for your homework, or, kind of a multiple choice question. So we good on that? Let's keep moving forward. So in the YouTube lecture, I talk about each type of decay and then do some examples. Here, I'm going to cover the 4 types of radiation that you're going to need to be able to do right balanced equations for. And we'll go over a couple more examples. But it's not going to be as in-depth as the YouTube video. So if you have an alpha emitter, that means that you have an element that's unstable, and when it decays, it's going to release an alpha particle, which is a helium atom, and you're going to form a new element. That new element is going to have a different mass number and a different atomic number. But what you must keep in mind, and this is for all nuclear equations, the mass number has to be balanced. So whatever your reactants are, the mass number and atomic number have to be the same when you add up everything on your product side. And that'll make more sense when we do some examples. With a beta emitter, you have an unstable nucleus that emits a beta particle. The mass number stays the same, but for the new element, the atomic number increases by 1. And this chart is this is only half of the chart. I broke it up over 2 pages. But this summary of the types of radiation would be another thing that's good to have in your notebook, to either print it out or just write out the different equations and label it like it is in the chart. We've got 2 more types to go. There's the positron emitter, and so this is very similar to the beta emitter, only this time your atomic number decreases by 1 for the new element. And finally, the gamma emitter, you're going to emit pure energy. So the mass number and the atomic number stay the same. You're not making a new nucleus or a new element. You're just releasing energy. So an example of that, so if you had a mass number of 99, let's say, an atomic number of 52, and you were this element, if you had extra energy, let me try writing that again because you can't see it very well. The way that you would indicate that there's extra energy there is an M. So an M after the mass number shows you that it's going to be a gamma emitter. And at the end of it, what you get is the same element. You just don't write the M after the mass number. And again, this is just we're going over these types, but we're going to do some examples. So I'm going to go through an example of how to balance an equation, and then I'll check in with you to see how we're doing. So this is an example of a question you might see. Write the balanced nuclear equation for the beta decay of cobalt-60. The first thing you're going to want to do is write an equation that depicts what's going on here. We have cobalt, and it's going to decay. We know it's going to make some new element that we don't know, and it's going to emit a beta particle. We know that because it's called beta decay. In beta decay, you emit a beta particle. That is the symbol for a beta particle. And that's why you need to know the symbols, so that when you read, you know the terms, you know the symbols, you can write it out. Now there's a key piece of information that we're missing here. We don't know the atomic number of cobalt. Pull out your periodic table and tell me what the atomic number is for cobalt. It's 27. More than likely, in these types of problems, you will have to fill in the atomic number from the periodic table. So I know I'm asking the same question about 5 times, but it's because I don't want you to forget. And when you're doing your homework or taking a quiz or doing an exam, those are the moments when you forget what you know. And something as simple as where is the atomic number, you don't want that to cost you points. Now we've got enough information to solve this problem. So we need to balance this equation, and we need to figure out what new element we form. Let's start by figuring out what the mass number is and the atomic number on both sides. So for the reactant side, what's our mass number? It's 60. If there was anything else over here, we would add the mass numbers together. So we're totaling up all the mass numbers on the reactant side. Likewise, for the atomic number, it's just cobalt, so it's 27. On the product side, it has to equal 60. We're not going to create neutrons or protons and just have them come from thin air and not account for them. So the mass number has to equal 60. The overall atomic number has also had equal 27. But we don't just have one particle or one element on this side. We have an element and a particle. We don't know what the new mass number is, but we know that the beta particle doesn't contribute to it. So if we don't have any addition to the mass number from that beta particle, that means that our new element is going to have the same mass number. Here, we've got a new element that's going to have an atomic number of something. And then we've got a -1 from the beta particle. What does our atomic number for the new element have to be if overall our atomic number is 27? It has to be 28. And the reason is, when you look at it, 28 minus 1 is equal to 27. So for a beta emitter, your new element is going to be the atomic number of the old element plus 1 to account for the fact that you're losing this high energy electron. We're not quite done yet. We know the mass number and the atomic number, but we can't write an atomic symbol just yet. We're missing the identity of the element. What piece of information do we use to figure out the identity of the new element that we formed? You have to use the atomic number. So your new atomic number for your new element is 28. And someone already put it in the comment. Our new element has to be nickel. So you look up that atomic number on your periodic table and you find the chemical symbol. Then you just write out what your mass number is and what your atomic number is. So that is going to fill in our blank. So the actual full equation looks like this. That is our balanced equation. Questions about that? Let me know if I need to go over it again or if there's a part of it that you don't understand. If you think you're ready to just try another example, you can let me know that too. And just a word to the folks that are hanging out in the background. If you don't tell me that you're not ready or you don't understand it, I won't know. Because all the people that are responding are saying they're ready. So don't get left behind. Even if you send me a private message or you send me a course message on Blackboard or something like that, let me know. Yes, go ahead. Okay, which part? Yeah, so that's the balanced equation. So that, let me go back to here. So we went over the types of radiation, and these are the different types of equations you're going to have to be able to write. That is the symbol for a beta particle. So in our problem, it said that the cobalt 60, it's a beta emitter, so beta decay. You have to know that beta decay means one of your products is going to be a beta particle and what that means. Okay? Great. You're welcome. Alrighty. So in the video, I did not go over a positron emitter. So I wanted to do that just to make sure that we had an example of every type of radiation. So you have a sample problem to reference for your homework and stuff. So for a positron emitter, we're starting with our magnesium-23. We're making some new element. And we're releasing a positron. That's that kind of anti-electron. So it's high energy. It doesn't have a mass number, but it's got a charge, or it's got a charge of +1. So its atomic number is 1. Just try taking a shot at this. See if you can figure out what the new element is going to be. And I'll give you the hint that the new element, its atomic number is going to be, you're going to subtract 1 from the atomic number here. So that's a pretty big hint. Give it a shot. I'll give you 2 minutes and then I'll check in. Let's get started. So we have to fill in the atomic number for magnesium. What's the atomic number for magnesium? It's 12. On our reactant side, we've just got the magnesium. So the mass number is 23. The atomic number is 12. We know that the mass number and atomic number have to be the same on the reactant side and the product side. So whatever new element and particle we have on the product side, when we add everything up, it's got to equal 23 for the mass number and 12 for the atomic number. The mass number, we've got the new element, which we don't know yet, and then we've got a positron, which contributes 0. A positron doesn't have a mass number. So we know that our new element has the same mass number as magnesium. For the atomic number, we've got our new element, whatever that atomic number is, plus 1. That 1 is from the positron. To figure out the mass number, the atomic number for our new element, you subtract the 1 from 12. That should give you 11. This tells you the identity of your new element. Yes. So, because this time we have a positron emitter, and that positron has an atomic number of 1. So while the atomic number, the total equals 12 on the product side, we've got the new element plus 1. So that's why I write it as an equation. So this 1 comes from the positron. Does that make more sense? It's one of those things you have to practice. So you have to do the different types of radiation and writing the balanced nuclear equations to get the pattern for each type. Okay. Okay, I don't see that screen sharing has been lost. Can everyone else see the screen still or no? Okay. We'll see. Blackboard has been interesting, so hopefully we don't lose it again. Alrighty. So we know our new atomic number. We know our mass number. We look up that atomic number on the periodic table, and it's sodium. So that's our new element. Now the question asks for a balanced nuclear equation. So if you were doing this for a chapter check-in, the final answer would be writing the whole thing out. So I know a few of you got sodium, but how did we feel, everybody else? How do we feel about this? Meh, okay, good. So we'll do more practice along the way, but if you have not watched that YouTube video, you definitely want to watch it. So it's one of those things where if you had exposure to it first and then we did practice, you'd be like, okay, that makes sense, or that makes more sense. But just to reiterate, you're going to want to know these types. So each problem that you do with balancing is going to be one of these 4 types: alpha emitter, beta emitter, the positron, gamma. Once you figure out which type you have, then you know what your products are. So in the last one, we had a positron emitter, and that meant that our mass number would stay the same, and the atomic number of the new element would be the atomic number of the old element minus 1. So you need to get comfortable with these types. It's not like, oh, well, we always add or we always subtract. Not the case. So unfortunately, we don't have time to do a bunch more examples, but we'll see how we're doing at the end. You'll get some more opportunities to practice writing this kind of balanced equation, because we still have some other types to go in terms of writing nuclear equations. And you're going to get some of that practice now. So we talked about decay. That's where you have an unstable nucleus. It releases some energy. Maybe it releases some particles. And then you make a new element. Maybe you have some particles on the other end. You can make radioactive isotopes by taking a stable nucleus and bombarding it with a small particle. And that process is called transmutation. So when we talk about nuclear medicine, there has to be a way to make this stuff. So one of the ways is by transmutation, taking something stable, hitting it with a particle, and making something else that's unstable. This is just an example here where you've got a stable boron atom and you hit it with an alpha particle. You make a new element, which is nitrogen, and it's unstable. And you also have a neutron left over. So you're not going to have to predict what the products are necessarily. But let's say I didn't include this product, but I told you that you make a neutron. You should be able to figure out the identity of the new element on the other side. And I'll show you what I mean. So we've got a radioactive isotope produced when we bombard this element with a neutron. And what you have to do is figure out what that new element is. That means the mass number and the atomic number and the element symbol. It's the same process that we did for writing balanced equations. The mass number for the product, or for the reactant side, is going to be 98 plus 1 because we have a neutron. So every mass number on the reactant side we're going to add together. And that gives us 99. Does that make sense so far? Because so far we've only had the one thing on one side. Now we've got multiple things on both sides. We're going to do the same thing for the atomic number. We've got 43. And then we've got a 0. I'm writing the 0 here just to show you that we're looking at both the element and the particle on the reactant side. Because this is a balanced equation, the mass number, the total, still has to be 99. And the total for the atomic number still has to be 43. This time, though, we've got a new element, and then we have the mass number of 4 from the helium atom that is released. Now it says it's reconnecting. Of course. See, when one person says, oh, I can't see it, I'm like, well, that means it's going to be reconnecting soon. So I apologize. Blackboard has been having some issues. It's not my internet, I promise. We paid the bill. No. So we'll just give it a minute. And we're getting so close to a break, too. After we finish this problem, it was going to be a break. So if you would like, we can take that break now. Or, because I threatened to break, it came back. You know what, Blackboard? Let's get through this problem. And then we'll see if you guys are ready for a break or if you want to press on a little bit more. Okay. So for our product side, mass number and atomic number have to equal what's on the reactant side. But now we've got a different element and a different particle. When we're figuring out the new mass number for our new element, you have to subtract 4 because 4 is already accounted for from our alpha particle. And the same for the atomic number, you have to subtract 2. Now we have the information to look up what our new, there's a hand. Positron. So think about it like solving an equation. If I told you 99 is equal to x plus 4, how would you solve it? Right. That's exactly what we're doing here. You're welcome. Alrighty. We've got our new atomic number, which means we can look it up. So that is our new element. Questions, comments, concerns? The key part is being able to figure out what your new mass number and new atomic numbers are for your new element if you're making a new element. But how do we feel? Better, worse, in terms of balancing these nuclear equations? Yes, what's your question? Let me see if I have... Okay, so there is another problem towards the end that we're going to get to do to kind of... is my way to kind of wrap back around and make sure that we get it when we talk about nuclear fission and fusion. So can you hold on for that, or do you need to do another problem right now? Okay, so let's just go over this one again, and then we'll move on, okay? Alrighty, let's choose a new color. So if I write something else, it'll show up better. So I think everyone kind of understands the mass number and atomic number on the reactant side. We're just adding things up. What do we have? On the on the product side, we're making a new element. So part of this equation we don't know. We know that the mass number and the atomic number have to be the same as the reactant side. But we're making two new things. We've got a new element and we've got an alpha particle. So with our mass number, it has to stay the same. It's 99, just like on the reactant side. But to get to that 99, we have some new element whose mass number we don't know. And we have the mass number. We have the mass number of the alpha particle. If you write that like an equation, it would be 99 is equal to x plus 4. You subtract 4 from both sides. 95 is equal to x. So that means that your new mass number is going to be 95 for this new element. You do the same thing with the atomic number. We know that 43 has to be the sum of the atomic number of the new element, we'll call that y, plus the atomic number of the alpha particle. The way you would solve that is subtract 2 from both sides. And that would be your new atomic number for your new element. So does that help a little bit more, writing it kind of like an equation? Good, I'm glad you got it. Okay. So we'll circle back around towards the end and make sure everybody's on the same train. We're going to switch gears a little bit. We're going to cover radiation measurements and do a couple of problems, and then I think we'll be in a good position to take a break. So we've covered so far types of radiation and writing balanced nuclear equations, either from an unstable nucleus decaying into making some kind of new element and a new particle, or we're trying to make a radioisotope. We're taking something stable, hitting it with a particle, and making something unstable. So that's what we've covered so far. Now we're going to talk about measurements of radiation, because you need to be able to measure some kind of concentration, activity. When we're talking about medicine or exposure, we're talking about absorbed dose, biological damage. So all of these things we need to have units and we need to be able to measure. This table will be your friend. In the YouTube video, I go over all the different types of measurements that you can have. I'm not going to do that here because we don't have the time. But this table summarizes very nicely the measurements, the common units for different measurements of radiation. So we have activity, which just tells you kind of how much radiation you have. So if you were doing an experiment and you want to use the same amount of radioactive isotope each time, you need to calculate its activity so that you can reproduce that. Commonly, you use the Curie for that. The SI unit is the becquerel. And then there's a relationship here that you're not going to have to memorize, but you will need to know how to use it. Then we have the absorbed dose. And this is, if I have this much activity in this radioisotope and I'm exposed to it, how much of that activity am I actually going to absorb? So it's like, how much radiation will be absorbed? So we definitely care about that. If you are someone who flies a lot, or if you know someone who's an airline pilot, stewardess, anything like that, you work in a power plant, you definitely want to know what your absorbed dose is. And there's actually these things called dosimeters that I talk about in the YouTube video that can show how much radiation you've absorbed. So if you're working with radiation on a regular basis, you are likely required to wear one because there are laws that govern how much you can be exposed to over a certain period of time. So this is very, very highly regulated because radiation can be deadly. There's radiation sickness. The final measurement is biological damage. Commonly, that's the REM. The SI unit is the sievert, and there's an equality here that relates those two. Again, this is very abbreviated. You'll need more information to do your homework, so make sure you check out the YouTube video. What I wanted to focus on is not so much the definitions of these measurements, but how to do some of the math associated with it. I'm going to let you do this on your own time. When I upload the PDF form of the lecture notes, I will complete this learning check so that you can check your answers. But this is just to make sure that you understand the different units of measure, and which ones, activity, absorbed dose, biological damage, which unit you're more likely to see if we're talking about these different measurements of radiation. So that was a lot of information. Are we clear on what you need to know in terms of just the measurements alone? Know what measurement goes with which unit. So is that okay? Yes. Yes. All right. So again, I don't want to spend too much time on this because that's something you can get from the video and from that chart. I want to focus more time on doing the math because I didn't go through and do practice problems for the math on the YouTube video. I wanted to do that live in class so that you can ask questions about it. So I'll go through an example, and then I have a very similar question next for you to try. So this is the math part, the real math part of Chapter 5. So the first thing we're going to do with this problem, let's label it. So we've got a sample of technetium 99M. And remember that M means that it's going to release gamma rays. So that's just a review. It has an activity of 1.5 curies. How many disintegrations occur in the technetium 99M sample in 5 seconds? So there's a couple of things that we need before we can solve this problem. One relationship that we need, which you will be provided, you don't have to remember this, is that 1 curie is equal to 3.7 times 10 to the 10 becquerel. And I'm terrible with spelling this, so I'm sorry, I have to go back. Okay, I'll just use the abbreviation. Even after all these years, becquerel sounds like it has so few letters, but it's got like probably double the letters that in my head I imagine it should have. Okay. So that's one relationship that we need to know. Because from there, we know that a becquerel we can relate that to disintegrations per second. So those are two relationships that you need to know. Now we can look at the problem again. We know that we have an activity of 1.5 curie. And what we need to know is disintegrations over 5 seconds. Looks like a complicated problem, but it's not. The first thing we're going to do is take our activity in curies and convert it to becquerel. Then we're going to take that and convert it in disintegrations per second. Once we have our activity in disintegrations per second, then we can calculate how many disintegrations we have in 5 seconds. So that's our plan. We're starting with our activity of 1.5 curie. The relationship between the curie and the becquerel, 1 curie is 3.7 times 10 to the 10 becquerel. I'm trying to cancel out curies. So should I put curies in the top or the bottom of this conversion factor? We need to put it in the bottom, which means that our becquerel goes at the top. So that's the first part. Now you've got to do this second part. I'm doing it in a different color. We need disintegrations per second. And we can relate Becquerel to disintegrations per second. It's a 1-to-1 type of deal. Now, when you're doing this calculation for yourself, you don't necessarily have to go through this step or show it, but I'm showing it to you so that you understand how all of these units are related. Now that we have our activity in disintegrations per second, we can take that and multiply by 5 seconds. So if we go through and cancel everything, we get rid of the Curies, we get rid of the Becquerels, and then we get rid of those seconds. And we're just left with the number of disintegrations. When you work out the math, that's what your calculator is going to tell you. But we can't have that many significant figures. We can only really have 2, because we've got 2 here in our activity, and we've got 2 significant figures in our time of 5 seconds. So that was kind of a lot. I want to give you a second to digest it. And then whatever questions you have, or if we need to go over it again, we can. So talk to me. Is this just a big ball of question mark? Do we need to go over it again? Or are there just parts of it that don't make sense? Or if you're good, you can tell me you're good. So we've got a big ball of question mark, and we've got some hands raised. Let me see if I understand your question. So what you're asking is, do we have to go through these steps in terms of converting activity to these different units before we can calculate the number of disintegrations? Is that what you mean? So you could have it be the opposite. I pulled questions from the test bank to give you a sample of the types of math problems you might see. So this is a representation of what you will see on your exam. So technically, yes, but you may not see that on your exam. Other specific questions is I can absolutely go through this again. And it seems more complicated than it is because of all the different units. If there's a question, go for it. And then I will go through the whole thing again. I will point that out as I go through the whole thing. Fair? Okay. So here's the problem. We've got a radioactive isotope with a certain activity that we're given in Curies. And we have to figure out how many disintegrations occur in 5 seconds. That's the problem. Before we can go to disintegrations, we have to figure out, we have to be able to relate Curies to disintegrations per second. And I'm just going to abbreviate disintegrations because that's a long word. So this is the key to the problem. Understanding these relationships. We know that 1 Curie is equal to 3.7 times 10 to the 10th becquerel. Another way to say the relationship between becquerel and disintegrations, it's 1 to 1. 1 becquerel, 1 disintegration per second. So we have to convert our activity from Curies to becquerel, and then becquerel to disintegrations per second. That way, we can use our time to figure out how many disintegrations in 5 seconds. We're going to take our activity in Curies and convert it to becquerel. So we use that equality. 1 Curie is equal to 3.7 times 10 to the 10 becquerel. Now you have your activity in becquerel. But that's still not exactly helpful because we need it in disintegrations per second. The relationship between becquerel and disintegrations per second, it's 1 to 1. So if we have 3.7 times 10 to the 10 disintegrations, it's the same thing as 3.7 times 10 to the 10 becquerel. I could have put 1 to 1 here. If we stopped here, then what we would have is our activity in disintegrations per second. So does that part make a little bit more sense than it did? It may not make 100% sense, but does it make a little bit more sense than it did before? Jordan, you said it was a big ball of question mark for you. Is it a smaller ball? Good. Let's just try to whittle it down. So if we stopped right here, we would have our activity in disintegrations per second. The question is asking for the number of disintegrations. So we have to take that activity, which is just a conversion factor, and multiply by our time of 5 seconds. When we do that, we're just left with the number of disintegrations. So does that part make a little bit more sense? We're not even talking about sig figs at the moment. I just want you to understand how we step through converting our activity to something more useful so that we can calculate the number of disintegrations, because that's all we did. I have another question that's pretty much this same question. So I think let's go to that one and see how we do. We'll walk through it together. Yes.
For that one, is that a -10 at the top? Or is it...
No, that's just a random pen mark. Let me try to erase that. That's why I didn't. Yeah. Yeah, no problem. Okay. So now we have a sample with an activity of 0.5 curie. And we want to figure out how many disintegrations there are. So without doing any math, do we expect the number of disintegrations to be more or less than what we had on the previous slide, where we had 1.5 curies of activity? More or less? If we have less activity, then we're going to have less or fewer disintegrations. So the number we get should be lower than the number we got for the previous problem. So let's just keep that in the back of our minds as we go through this. We have to relate our 0.5 curies to some number of disintegrations per second. The way that we're going to do that is to go from curies to becquerel, and from becquerel to disintegrations per second. Our equality for the first one is 1 curie is equal to 3.7 times 10 to the 10 becquerel. For the second one, I'm just going to simplify it because it'll take a little bit less room. 1 becquerel is the same as 1 disintegration per second. It's the same thing as on the other slide, okay? So let's do that part first. So this is figuring out our activity in disintegrations per second. What is our first conversion factor going to be? If we're going from curie to becquerel, and we're using this first equality, what conversion factor do we need? You can just tell me like Curie over Becquerel or Becquerel over Curie or something like that. Don't worry about trying to get that big number in there. That's not easy to type. We're going to put the number of Becquerel and 1 Curie on top. That's the unit that we want to move on. We're going to put the Curie in the bottom so that it cancels out. So that's step 1. Now we need to go from Becquerel to disintegrations per second. What am I going to use for my conversion factor here? And this is our equality for number 2. What's my conversion factor? Yeah, we're going to want those disintegrations per second on top. And the Becquerel on the bottom. Because we want to get rid of the Becquerel and move into disintegrations per second. So when we cancel our units out, we should get disintegrations per second. Put that into your calculator and tell me what you get. So you should get 1.85 times 10 to the 10 disintegrations per second. So all we did was figure out we had 0.5 Curies, and we figured out that that equals 1.85 times 10 to the 10 disintegrations per second. Now we need to take this and figure out how many disintegrations occur in 5 seconds. So your calculator is going to tell you 9.25 times 10 to the 10. But we can only have 2 sig figs here. So does that problem feel better than the first one? Good. So I think this is a good time to take a break. We'll take 5 and come back at 12:47. Alrighty. Before we move on, are there any other questions about this type of problem? So you'll definitely want to practice. Do your mastering chemistry homework. Come to office hours, that kind of thing. But are there any other specific questions about this problem? Yes, it is an exact number, the 3.7 times 10 to the 10. So we're going to move on and do a different problem type, one that's a bit less complicated. So I alluded to the fact that there's nuclear medicine. Iodine 131, which is the topic for this problem, is used to diagnose and treat thyroid issues. So this problem says the recommended dosage of iodine 131 for a test is 4.2 microcuries per kilogram of body weight. How many millicuries should be given to a 55 kilogram patient? And then you have an equality here that relates millicuries to microcuries. So remember, that funky looking M is micro. So let's write down what we know. We've got 4.2 microcuries per kilogram as the recommended dosage. We have a 55 kilogram patient. And the question is, how many millicuries should we give to the patient? Overall, what we're trying to do is another conversion. We're taking the dosage, which is a conversion factor, to figure out how much of this radioactive isotope we should give to the patient. Once we do that, we have to report our answer in millicuries. So here's the plan. We're going to use the dosage to calculate how much to dispense for the patient. And that's going to be in microcuries. That's step 1. Then we're going to convert our microcuries to millicuries using the equality that's provided. How would I figure out the dosage or how much to dispense to the patient if I'm given the dosage and the patient's weight? There's only a few different operations we can do. Add, subtract, multiply, or divide. We've got these two numbers. Which one of those things are we going to do to figure out the number of microcuries to dispense? Yes, multiply. I think more people are still on break. So we're first going to multiply these two. You've got 4.2 microcuries per kilogram times 55 kilograms. The kilograms cancel, and you're left with the number in microcuries. So your calculator is going to tell you that. But we can only have two significant figures. But we're still not done yet. Our units are in microcuries. The question is asking for millicuries. So if we stopped there, the answer would be wrong. We need to use that equality to write a conversion factor. We have to divide that number we got by 1,000. And that's our final answer. How did that question feel? Hopefully substantially easier. Way better. All right. So now I want you guys to do this problem. I've changed the numbers on you. So your recommended dose and the weight of the patient are different. And there's a different number of significant figures. So take note. I'll give you 2 minutes and then we'll go over it. Let's get started. If you're still working, that's fine. I'll go slow. And as you get your answer, you can still put it in the chat. This time our dosage is 4.25 microcuries per kilogram. And our patient is 75.6 kilos. We still want the number of millicuries to dispense. We're going to multiply the dosage by the patient's weight. And that will give us the number of microcuries. Your calculator is going to tell you 321.3. You're going to say, thank you, calculator. However, I only need 3 significant figures. So you've worked too hard. And I'm going to drop off that decimal place. Now we need to convert the microcuries to millicuries. So what you do here is divide by 1,000. And you get 0.321 microcuries. So I know a few of you got that answer. How did that feel? Good? Feel like you're ready to, you could do that type of problem on your own? So the key here is recognizing what you can do with the information. You're given a dosage and a patient weight. You can figure out, it could be millicuries, it could be milligrams, it could be whatever. It's the same type of problem. We saw this type of problem in chapter 2, where we had a dosage of medication in a certain number of milligrams per kilogram of patient weight. Same exact idea. Only this time we're talking about activity. So we're going to move on to the concept of half-lives and then do a couple of problems with half-life. So radioisotopes decay over time. That means eventually they're going to stabilize that nucleus by emitting some energy, releasing a particle, what have you. The amount of time that it takes for the radiation level to decrease to 1/2 of its original value is called the half-life. Again, I mentioned the iodine 131. It's used for medicinal purposes. And it has a relatively short half-life, 8 days. So if you're starting with 20 milligrams of iodine 131, in 8 days, you will only have 10 milligrams of that radioactive iodine left. If you wait an additional 8 days, you will have 5 milligrams of iodine left. And another 8 days still, 2.5 milligrams. So that's how a half-life works. You divide your amount by 2 for each half-life. The half-lives of radioactive isotopes are different depending on the isotope. And in the YouTube lecture and in your book, there's a table of a lot of different radioisotopes and their half-lives. And it'll tell you kind of the purposes. Some of them are for carbon dating. Some are used for medicinal purposes. So it has a lot of good information there. So I'm going to go through this one problem, and then I'll let you guys do a problem, just to make sure you understand the concept of a half-life. So carbon-14, it's used for carbon dating. So fossils, any kinds of remnants of ancient civilizations, things like that. And it was used to determine the age of the Dead Sea Scrolls. If the scrolls were determined to be 2,000 years old, and the half-life of carbon-14 is 5,730 years, what fraction of this half-life has passed? The key here is knowing that you can write an equality to show how many years or days or seconds are in one half-life. And we're told this in the problem. Now, I abbreviate half-life with HL. So one half-life is equal to 5,730 years. That's your equality. You can write conversion factors from that equality. So we just take that equality and write two fractions. We're given that the age of the Dead Sea Scrolls is 2,000 years. And we're asked about the half-life. If I want to figure out the number of half-lives, which conversion factor am I going to use to do that? A or B? We're going to use A. We're starting with our time, which is 2,000 years. We're going to multiply and divide. So you multiply by 1, divide by 5,730. And your calculator will tell you 0.349. How many significant figures are in 2,000? There's only one significant figure here. So that means for our answer, we can only have one. So a third, about a third of a half-life. That's our answer. Does that problem make sense with using a half-life? Okay. Yes.
Okay, so when I started that homework, it said something about like how much is like fusion like is active,
Mm-hmm.
and like from like the amount of time was it like put into the amount of the like half life. So say if like 6 hours and the half life was like 3. So like okay, so that one go with the equal, and then it was another one. I can't really remember, but it didn't go in equal, so I didn't think it in like that. I mean, I didn't know how to do it. So it's like, how would you do that? Is this like an example of how you would do it?
So I have a problem like that on the next slide.
Okay, okay, thank you.
Yep. So this one, it goes in evenly. For your exam questions, I don't think it's not going to be 2.7 half-lives or something like that. But it's not that difficult to figure out. So if you still have questions about that, Ayana, let me know after class. I'm going to run through this problem and show you. No problem. I'm going to go through this problem and show you how to do it. Because we're running a little bit sort of short on time, and I want to make sure that we get to nuclear fission and fusion. So we're given a different isotope of iodine, I-123, and its half-life is 13 hours. We're starting with the sample of 64 milligrams, and we want to know how much do we have left after 26 hours. The first thing that you want to do is take the amount of time that's elapsed and convert it to the number of half-lives. To do that, we're going to take our time, 26 hours, and we can write a conversion factor to say 1 half-life, or this is an equality, excuse me. 1 half-life is equal to 13 hours. So just like in the problem before, we're going to use a conversion factor that has half-life on the top and then what that half-life equals in hours on the bottom. You divide 26 by 13, you get 2 half-lives. You're starting with 64 milligrams of your isotope. After 1 half-life, how much will you have left? You'll have 32 milligrams left. So you divide by 2. That's all you're doing. If we have 2 half-lives, we're just dividing the 32 by 2 again. That gives you 16 milligrams, which is our answer. When it comes to doing the uneven amount of time, so if you look at, we're dividing by 2 and then dividing by 2 again. That's the same thing as saying that we're dividing by 4. So there's another equation that you can use that takes into account an exponent. It's not in your book, but that is the easiest way to do it. And if you need help with that, I can help you with that either directly after class. Well, I have another class to teach, so I can do it for like 5 minutes directly after class, or I can help you in office hours. But does everybody get the general idea of calculating the number of half-lives and then computing how much of a substance you have remaining? Because that's all we're doing. Okay. So like I said at the very beginning of class, which feels like eons ago, there are lots of medical applications. I'm not going to go into all the different imaging techniques. That's in the YouTube video and it's in your book. So you will need to go over that to do your homework. But I will address just the overall kind of why it's used in medication. So we use radioisotopes with short half-lives. And the reason for this is your cells do not differentiate between radioactive and non-radioactive atoms. So whatever is there, they're going to use. And once you incorporate a radioactive atom into a cell, those atoms are going to emit radiation. That's helpful when you're trying to get an image. But remember that radiation, we're giving off energy and we're giving off particles. And those particles can then bombard other atoms. So you can do some damage to your cells. You don't want a radioactive isotope in your body for years on end. You want to use something that's going to decay within a few months of use to minimize the amount of damage that happens to your organs. So radioisotopes are great for imaging. You just have to be careful with the dosage and which radioisotopes you use so that you minimize the damage. So here's a quick learning check. Which of the following radioisotopes are most likely to be used in nuclear medicine? So for A, we have a half-life of 1.3 times 10 to the 9 years. Are we going to use that in nuclear medicine? Of course not. Way too long. What about 12 hours, if there's a half-life of 12 hours? Yes, that's pretty short. And for iodine 131, I've already said that it's used. So yes. And again, the reasoning is you want a short half-life so that you're not emitting radiation for years on end and doing damage to your organs. The last topic that we need to cover is nuclear fission and fusion. Nuclear fission, what we're talking about is taking an unstable nucleus you bombard it with a particle. And then you create new elements along with more particles. So what's shown here is uranium. You bombard it with a neutron and you create an even more unstable nucleus. Eventually, you're going to get decay. And in the case of uranium, you create krypton and barium, along with a lot of energy, which is what this kind of sun-looking thing is. And you make more neutrons. Because you make more neutrons, if you have more of your initial isotope, you can initiate what's called a chain reaction or a nuclear chain reaction. Because these 3 neutrons can be combined with 3 more atoms of uranium. That's fission in a nutshell. You're bombarding a nucleus, making an even more unstable nucleus, and then eventually that nucleus will decay. You'll make new elements, particles, and release a lot of energy. That's the basis for a nuclear power plant. So you're creating a lot of energy, and it's a reaction that can just keep going and going and going until all of your fuel is spent. Nuclear fusion is kind of the opposite. You're taking 2 small, stable nuclei and you're crashing them together. You're going to make one larger nucleus. So one new element. You're going to take 2 small nuclei and combine them to make one new element. You're also going to produce some particles and lots of energy. So if hydrogen isotopes are combined, like in this example, you create helium, a neutron, and a lot of energy. This is the reaction that goes on in the sun and other stars like it. It requires very, very, very high temperatures. I didn't go too much into detail here. I don't include that much more in the YouTube video. But after you watch the YouTube video, I want you to try this learning check to make sure that you understand the difference between nuclear fission and nuclear fusion. I will, of course, make sure that the answers are in the PDF that I upload. This last learning check is kind of like a review of both nuclear fission and writing balanced nuclear equations. So I want to go through this one really quickly and then do reminders, and then we'll be done. So we talked about nuclear fission and how you take a particle, you bombard a nucleus, And then you can create some new elements, some particles, and release a lot of energy. Just like we did at the very beginning, you total up all of your mass numbers. And I'll try to do this in different colors. So, for our reactant side, we've got 1 plus 235. So our total is 236. For the atomic number, that neutron doesn't have an atomic number, so its contribution is 0. But I write it anyway just to show you that you take everything that's on the bottom and you add. So our total atomic number on the reactant side is 92. Let's do the same thing for the product side. We know one of our products has a mass number of 137. We don't know the other element that's made. We'll call its mass number X. We've also made 2 neutrons that each have a mass number of 1. So that's going to be 2, right? So if we rewrite that as an equation, we know that we have to have 236 because that's what our reactant side is equal to. That's what we have left. And you solve for X. And I'll tell you that X equals 97. For the atomic number, it's a very similar thing. So we know that our new atomic number for the element is 40. You look up what element that is, and that's zirconium. So that should be kind of a culmination of the very beginning almost and the very end of what we talked about. So make sure you can do that problem. And last thing is reminders. And then after that, you can ask questions or go if you need to. Chapter 5 check-in, mastering chemistry for Chapter 5. All that is due on Sunday. It's not a super huge chapter, so hopefully you'll be able to get through it more easily. Make plans to watch the Chapter 6 video, which I'm already working on, in preparation for class on Tuesday. You have an exam next week, which is exam 2, and it's going to cover chapters 4 through 6. Unfortunately, with the way that our schedule is condensed, this is the only way that it was going to work. So, you have an exam next week that covers part of what we're covering. So we'll do some exam review, and we'll also talk about Chapter 6. But it would behoove you to watch the Chapter 6 video and get started on some problems before Tuesday. So I've already got the presentation made. I just got to make the video, which will happen tomorrow morning, and it will be posted Wednesday, which is tomorrow afternoon. Try to give you as much time as possible to read it, to watch it and take notes. So please, please, please take note of that. Exam 2 covers chapters 4 through 6. We're covering chapter 6 on Tuesday, so you need to come correct. If you have any other questions, let me know. Otherwise, you're free to go. Yes.
Will we have any documents that we can use on the test like we did last time?
Yes. So I will give you it'll be exactly like last time. So you'll have a periodic table, and then you'll also have an equation sheet, and you print those two things out before you start your exam. You're welcome. Feel free to ask any other questions you have, or otherwise, have a good day.